Okay, now we're on step 2813, and we're kind of ready to run the experiment. Unfortunately, we are not able to do the experiment, but we're going to learn how to manipulate this equation. So if we had the suspended mass to be 30 grams, and we find out from the experiment that the angular acceleration, as we mentioned, it's negative, is 0.774 radians per second square, and we measure the pulley radius, that capital R, to be 14.5 millimeters, so there's some conversions to be done. Then in the next step we can kind of compute the moment of inertia for the system. Okay, so that's the equation. Again, m is 30 grams, it's going to be 0.030 kilograms, and g is our gravitational acceleration, 9.81 meters per second square. Since the radius is in millimeters, you need to divide that by 1000 as well, so you're getting 0.0145 meters. And divide that by alpha, angular acceleration, it's negative, so there are two negatives. The first term is going to be positive then. N minus mr squared, m is again given, r is given. When you plug these in, you're getting the system of the moment of inertia for the system to be 5.51 times 10 to the negative 3 kilogram meters square. Okay, so here's a quick question on the clicker question on Canvas. Please answer this. And next, we are trying to determine the moment of inertia for point masses, which we can then compare to the theoretical result, which says that for a single point mass, I is equal to mr squared. And so we're gonna find a way to find a way that we could use find the moment of inertia for just the point masses. So what we can do is we can remove the point masses, right? And then run the experiment again with only the rod and the pulley. So if you look at the figure once again, so we had those pulley mass attachments on each side. So take them off and run the experiment. You can change the hanging mass, doesn't matter, and we will do so. So we're gonna use 5 grams of hanging mass, okay, later, and we can calculate those alpha, and r doesn't change. The pulley radius is the same, so we can find out the inertia that way without the masses, right? And since this inertia we found in section or item 28.14 is for the system, and now we know the inertia without those point masses, the difference is going to give us what the total of the point mass inertia is. But there are two of them, so then we're going to take half of it to figure out theoretical value, and we're going to compare it with the so this is the experimental value because it comes from the experiment, and we're going to compare with the theoretical value from the moment of inertia equation, mr squared. Okay, so that's what we're going to do. So first thing we do is we run the experiment again without the masses. Just pasted this equation here that we find out. We will use it again. So now the hanging mass is 5 grams. The pulley radius didn't change. The angular acceleration is different, of course, now, right? It's much faster. It's much bigger. Spins faster, but still negative. Now, if you plug these in here on the equation for inertia, you can find, as we call, I no mass. Okay, so we kind of got rid of the masses on each side, and this inertia is the inertia of the rest of the things that spins, okay, as a system, but except those two masses. So this value is found to be, as you can see it right here, 3.55 times 10 to the negative 4 kilogram meters per meters square. So it should make sense. It is much less than what we find out earlier, right? This was what we got for the system. This is 10 to the negative 3. This is 10 to the negative 4. And because we have less mass and less inertia, right? So what we need to do is to find the point mass inertias, but again, remember that there are two of them. So we're finding those two inertias, and what we need to do, we have the system's inertia minus that everything but those two masses is gonna give us the inertia of those two masses, okay? And we're getting the answer as this, okay? Again, this is 10 to the negative 3, but it's not the same as before, of course. So next thing we should do is to check. So this is our experimental answer, but this is for two masses. So if each mass, in the next step, we are calculating the theoretical value. If each mass is 75.4 grams, and the distance from the pivot point, I'm going to go back up here again to the figure. So the distance we're talking about is from here to there, okay? So this is, let's call it D maybe. And there are equal distances from each side, equal masses as well. So we are going to apply these to the equation. This is mass, this is the radius, again, this is in centimeters. So we need to convert to meters, and that's we do it right there. We know that the moment of inertia is mr squared, so we just plug those in, grams to kilograms as well, right? Divide by 1,000, and you're getting 2.443 times 10 to the negative 3 kilograms meter square. And again, this is for one of them. Two of them, you get this, right? This is multiplied by 2. So if you multiply this by 2 or divide that by half, then you can find out what the inertia is. So what we did here is we multiplied this by 2, and now these two, let's use something different. These two are comparable. This is the theoretical value. At the bottom, we have the theoretical value. At the top, we have the experimental value. And you can even find the percent difference, which is 5.5%. It's not much. It's acceptable. And kind of just to show you how you can figure out the inertia of unknown shapes or system piece of there's several masses, several mass distributions in it. So kind of one of the things that we use here is that the inertia is additive, right? So it's like mass. So you have 50 grams, you add another 50, you get 100 grams, right? Total mass is 100 now. You keep adding. Inertia is like that too. So you have the objects like the rod, the pulley, the hanging mass. You find that inertia as the inertia of no mass. And you already had the inertia of everything, including those two masses. Now subtraction will give you the difference, and the difference is those 2 point masses, and that's what we did, and we compared it with the theoretical value. Again, there's another clicker question. You're gonna answer that on Canvas, and I'm gonna skip the rest of the things. So 28.22 is skipped since we're not able to show any data. And the most of, like, I think the entire page of 348, so we're skipping from right here 28.23 all the way to 36. These are going to be skipped as well. You're welcome to take a look at it. I'm not erasing anything. There's a little bit more details in here. So if you had a, like, if you're attaching a ring and such, so it's like you can see that it can get more complicated with some changes. But what I want you to do is like kind of look through these clicker questions, and I'm gonna add these. These are on Canvas, so you can just do those on the Canvas. And here's our summary again. So hopefully that's clear now that the rotational form of Newton's second law is sum of torque equals to I alpha. Okay, and you don't need to memorize it. Think about the mapping. F goes to torque, M goes to inertia, and A goes to angular acceleration alpha. If the net torque on an object is 0, the object rotates at constant angular velocity if it was already rotating, or remains stationary if it was originally stationary, and we call this as equilibrium. Okay, so it's in balance. or there's an equilibrium. The key thing is angular acceleration is 0. Okay, that's why the speed is constant, but if it already had a speed, it will keep that speed constant. If it was 0, then it's going to remain 0. So conversely, if the angular acceleration of an object is 0, the net torque on the object is 0 because of that second law here. And in general, we calculate the torque as R cross F. And torque is a vector as well. In R and F are vectors. You can find the magnitude as RF sine theta, or if you are given unit vector notations, we've done all of those calculations. You can also use determinant to figure things out. Remember those fish swimming to the right, to the left, and then right again. So revise those as well if it is not clear yet, and please ask questions this week. And we can use simple setups and Newton's law in rotational form to determine the moment of inertia for any shape. So not always they're going to give you the moment of inertia. If you know a known shape, you can use the table 10.2, or if it is a point mass, you can use the equation sheet. It's simply mr squared. But if it is something else, if it's more complex, or it's made of a bunch of things like that, like just the previous problem that we solved, but step by step. So you can also use maybe the second law to figure out what inertia is. Again, we practice that. So the experiments show that the theoretical equations for the moment of inertia are in good agreement with the measured values. Okay, so, and that's what we also showed. We had like about 5% error, but it is acceptable. So this is the end of today. Again, I'm gonna add more problems later, but I want you to really understand the concepts now. So if you have any questions, once again, please don't hesitate to reach us out. You can, if it is Monday, Wednesday, Friday, you can just let us know. Try to do it before the office hour time. Let us know that you want to meet with us. If not, Tuesday and Thursday we'll be there. You don't need to let us know. You just need to drop in.